holes and quantum computers. So Professor Marika Taylor is a very distinguished and extremely active and potent member of the international science communication community while still carrying out groundbreaking research on particle physics, black holes and string theory. Some of her academic publications that I sort of checked out while I was trying to understand what to say about her in this book are about fuzzballs with internal excitations. And a little fraction of a second I thought that might be about me, but apparently not. And then there's another one which I like, was on the anatomy of bubbling solutions, which has nothing to do with tea. Anyway, I think Marika's going to say something more about quantum computers now. So, give her a big welcome.
So thank you all for coming on such a kind of drizzly evening. Indeed, I'm going to talk about black holes and quantum computers. So it's a kind of shift in focus from the previous talk. So I'm going to be discussing some very surprising relationships between fundamental science, looking up in the sky and thinking about black holes, and actually the technology of the 21st century. So, as I said, kind of a complete change of focus in some ways. So I'm going to start by sort of, really reviewing what Poshak said. I know it's only like 20 minutes, but you've had some beers since then, so I'll be saying some of the same things in slightly different ways. So you all have images of black holes that you know from science fiction movies, science fiction TV shows. So this on the right-hand side, that's an image of Doctor Who who was in a stationary orbit around a black hole. When they get bored of Daleks and Cybermen, they think, okay, black holes, so there. You've seen already this evening the picture from Interstellar, where a black hole was basically the main uncredited character, in the credits of the movie. And on the left-hand side, this is just to sort of tell you that you know the scientific terminology already. There was a movie 20 years ago called The Event Horizon, and actually a lot of my talk is going to be about what happens at the event horizon of the black hole. So, what is a black hole? So we had a lovely introduction to this already from Poshak, but for me the defining feature of a black hole is going to be the fact that nothing can escape from within it. So if we try and throw something off the surface of the Earth, we know that if we throw something fast enough, it's going to escape off into space. But as you make something smaller, while keeping the same mass of it, the escape velocity actually increases. And we know from Einstein that there's a limit. We can't throw something faster than the speed of light. So a black hole is something for which the escape velocity is faster than the speed of light, is higher than the speed of light. So nothing can escape from within it. So Poshak's been talking about lots of interesting astrophysics effects that happen outside the black hole. So there's all kinds of things going on outside the black hole's event horizon, but nothing can get out, according to this argument, from inside the event horizon. So it's a really interesting place. So beautifully illustrated by our group's kind of space-time trampoline. I didn't know it was called the space-time trampoline, actually. I thought it was just, we have other names for it, but beautifully illustrated by that is the effect of gravity, according to Einstein's theory of gravity. So something like the sun, a star like the sun, very heavy. So according to Einstein's theory, it curves the space around it, and that's what's shown in this picture over here. Oops, sorry, go forward. So that's what's shown in the picture, and if you play with the sort of balls on the trampoline, you can kind of see this effect. But now if you have something which is smaller, the same sort of mass, but actually smaller, it's more dense, it's actually going to curve the space-time more. So I think later on this evening we're going to hear about neutron stars. These are things which are going to be smaller and more dense, and they curve the space-time more. And Poshak's definition of a black hole was something which was, so dense that it, effectively it warped the space-time, that much more. It warped the space-time a great deal. And so for a black hole, the defining thing is indeed that, we've got this, huge warping of the space-time. If we fall in here, we're like falling down a huge throat. But there's a point of no return. So if we pass this point, the event horizon, then, according to, the rules of classical physics, we're never going to actually be able to escape from this. So Poshak has talked a little bit about how we detect black holes. So I'm going to sort of mention this, again, really from the perspective of saying what we know about what happens around the event horizon itself. So the earliest evidence that came for black holes was, as he showed beautifully with his movies, the fact that we could see things orbiting around things which were invisible to our telescopes. So this is actually a screenshot of the movie that he was showing. So you can see, stars moving around something, and you can infer from watching this over a period of years how heavy is the thing in the centre. But of course, when we infer the existence of a black hole like this, because we're not directly detecting them, we don't know too much. We're not going to learn much about what's actually happening close to the black hole itself. Now, the picture that is shown in an interstellar, this is a picture, an idealized picture of what we expect that a black hole would look like. As Poshak explained, we've got the accretion disk, we've got the warping that causes us to see, the light emitted from behind the black hole pulled towards us. We expect jets coming out as well. But we don't have at this point. We're hoping to have, over the coming period, much more accurate data coming from telescopes, which would kind of display this sort of picture. By the way, something that Poshak didn't sort of talk about too much. This, of course, is an image which is touched up for the movie. It was, I think, touched up in the studios in London, actually. But I mean, there are real physics simulations which underlie it. So some of the physics simulations underlying it come from Kip Thorne. Now, Kip Thorne, some of you might sort of heard that name because when there was an announcement made of the gravitational wave discovery last year, Kip Thorne was one of the people involved in that announcement. So, as Poshak explained, if you could actually get close enough to a black hole, if you had the sensitivity to actually image it, you would see all kinds of interesting things, and that's what the next generation of telescopes is actually looking for. So you're going to see the interesting behavior of the accretion disks and the jets. But again, the physics I'm interested in, the physics of what happens towards the event horizon. This is something that you can barely see from the back of the room here. It's swamped by these accretion disks because my event horizon is sitting down here. It's this little black dot. And the little black dot is saying that, from within the black hole itself, nothing is actually coming out. So all kind of fascinating things happening in the vicinity of the black hole, things being sucked in. But, if we're really keen on seeing or knowing about the event horizon, we've got to actually get a picture that is really that good to see what's going on down there. So, it's a really hard problem, to actually understand the behavior deep down at the event horizon. So what is our best hope? So I have to say this, my own group works on gravitational waves a lot. So last year there was the announcement by the LIGO experiment that they had discovered gravitational waves. So gravitational waves predicted 100 years earlier, almost immediately after Einstein wrote down his equations for gravity, people determined that there would be gravitational waves. And so what they had seen was the following. So in September 2015, what they observed in their detectors was a collision between two black holes. The black holes involved in the collision were 30 to 60 times as massive as our sun, so they're pretty heavy. And they could figure out from the gravitational waves that they saw that collision took place about 1 billion years ago. And the gravitational waves which were created in this collision, so just in a tiny fraction of time, had 3 times the energy of the sun. So Poshak talked about huge energy scales being involved. So this collision took place in such a short space of time, and yet threw out 3 times the energy of the sun. So much energy was thrown out in ripples of the space-time that we could actually see it 1 billion years later. So, what do we mean by gravitational waves? So this is a simulation. I hope it's going to work. So the little black dots that you should be able to see at the centre, in the back of the room, these are the black holes. And what's going to happen in this simulation is that the black holes are going to move around each other, and they're going to collide and form one black hole. And what you're going to see on the blue area is the curvature, how much the space is curved around the black hole. So every time you see kind of ripples of space, you're stretching and squeezing of space, that's the gravitational wave. Okay, let's see if this is going to work. Yep. So they're moving around each other, And you see, that the space is becoming more and more curved. They're moving closer, they're spiraling towards each other. And look at the time scale. We're talking sort of tiny fractions of a second here. The movie's sort of going slower so you can see more details. I should say this is a real scientific movie, for people to see the details. Now at this point, this is the point where they've actually merged and formed one black hole. And now, what's happening, you can see these huge kind of pulsations, so up and north, these black and pink, blue and pink areas. This is the ripples which are being caused by this collision. So this is what LIGO actually saw. They saw the ripples of the space coming from this collision, the stretching and the squeezing of space that came from this collision. Okay, so if one looks at the signal that they saw in the detectors, the signal that they saw was precisely the same kind of thing that we've seen here. So at the beginning of the merging, there's a sort of a gentle vibration of the space, and then just after the thing has merged, it's a much bigger vibration. And that's the signal that they actually saw here. And they have two detectors, because if you saw something in one detector, you can never be quite sure that it wasn't caused just by some sort of local seismic things, local kind of earthquakes. You see the same thing in two different detectors at different places on the Earth, and it's exactly the same shaped signal, which you can even see by eye here. It's the same shaped signal. You're more confident that it came from outside the Earth. If you see it with more detectors, so there's more gravitational wave detectors being built, again, you can do much better at figuring out exactly where it came from in the sky, when was it produced, and so on. So why are black holes so interesting? Why are gravitational waves so interesting for those of us who are interested about what goes on at the black hole horizon? So the movie I just showed you, you saw that a lot of the interesting gravitational waves were produced at the moment where the two black hole horizons had actually merged into one. So it's very, very sensitive to what is going on at the black hole horizon. So this one detection almost gave us more tests of the theoretical considerations we've been working on for 40 to 50 years. One detection there gave us more information that we've had from astrophysics on specifically what's going on around the black hole horizon. So as Stephen Hawking said, gravitational waves provide a completely new way of looking at the universe. And he was very excited by this discovery, I have to say, because he saw this. He's been working on black holes for 50 years now, and he sees gravitational waves as being, one of the realistic ways to actually test many of the things that he's been working on. Okay, so what I'm interested in really in this talk is a very basic question. Probably not one that many of you spend your time worrying about. You might worry, am I going to fall into a puddle? I'm going to fall into a bus. But those of us in physics departments sometimes worry, what if we happen to be passing by a black hole and we fall in? So this is an image from nature. This is the astronaut. What actually happens when you fall inside a black hole? Okay. So, the traditional Einstein point, which you are all experts in, so I'm not going to spend too much time on, because how many people here like sci-fi movies? How many people have seen Interstellar? I'm not spoiling the plot. Many of you have seen Interstellar. Okay, and many of you have seen Doctor Who and related things. So it's not uncommon for people to fall behind black hole horizons and for all kinds of interesting things to happen in these kinds of movies. And, the traditional viewpoint, which would have come from, our understanding of Einstein's theory of gravity, is that when you fall behind the horizon, you see some kind of weird Doppler shifts. People have thought about this. And then you feel, as you're falling deeper and deeper inside, basically you start being stretched and pulled in all kinds of directions. You have tidal forces, as we call it, and they basically rip you to pieces. So you're pretty much doomed. But immediately after you've fallen, you don't really notice much, except some kind of weird Doppler type shifts. So that's often what's portrayed in movies, I should say. So let's think a little bit about this. So this is a kind of a bit of a change in the sort of picture. It's a sort of similar picture to what I showed before, showing that black hole is something that's so small and heavy that it's just, distorting, it's warping the space so much. So everything outside in the green area, this is the region, that Poshak was interested in, lots of interesting things happening there. But I'm asking what happens when you pass this point of no return, you pass beyond the event horizon into the deeper region. And so the traditional answer here is that, space becomes more and more curved, and eventually the curvature is just so large that Einstein's theory isn't valid anymore. You need some quantum physics. So, beginning of the 20th century, there were two huge developments in physics simultaneously. One was quantum physics, and one was Einstein's theory about what happens when you move to close to the speed of light or you have strong gravity. Two of them are different things. So one is the classical physics of what happens when you move fast or when you're talking about strong gravity, and the other is about quantum physics, things that happen inside atoms. And the idea is that deep inside a black hole, you need to put those two things together, and you need a quantum theory of gravity. And so for those who are kind of pushing the frontiers of physics, black holes are fascinating because this is one of the places that we know that we need to reconcile quantum physics with gravity. So the modern perspective actually on this is that the traditional Einstein viewpoint, which has prevailed perhaps for 50 or 60 years, that you fall into the black hole and you don't immediately notice, you just see some weird Doppler shifts and you fall deeper and deeper inside. The modern viewpoint is that this is probably not correct, that there are already very, very large quantum physics effects happening as you go to the event horizon. And that's why I emphasized the lack of experimental evidence for what's happening at the event horizon. We have virtually no evidence, even what's happening close to the horizon, let alone about what's happening inside. So the modern viewpoint is that there's some very weird quantum physics going on at the event horizon itself. So let me tell you where that comes from. So actually it goes back 40 years or so before I was born. This is Stephen Hawking when he was rather younger. So in 1974, he kind of realized that quantum physics was going to play a very important role for black holes. So although classically it's true that nothing can escape from the black hole because nothing can move faster than the speed of light, quantum physics says that there's all kinds of uncertainty, right? So quantum physics says you can never know exactly how fast something is moving unless you want, you can't know position and speed precisely. And so if you take into account quantum physics, it's actually possible for black holes to radiate particles. So that's his big discovery. That's the one for which he would like to win the Nobel Prize, but as I said, it's pretty hard to test this, so probably not going to happen. So the black hole horizons, I should say, they still nonetheless effectively still look black for our telescopes because the rate at which particles comes out is really slow. But nonetheless, quantum physics let the particles escape. But immediately after he realized that black holes could, quantum effects could let black holes emit particles, he realized that there was a kind of an intellectual puzzle, which he called information loss. So the puzzle is the following. You take your obsolete computer and you throw it into a black hole, as we do over here. Now, if you wait long enough, that black hole, it will be really, really slow, but that black hole will eventually give out all kinds of particles. It will evaporate into a bath of radiation. And the problem he realized was that in sort of reconciling Einstein's theory with quantum physics that he was using, was that there was an information loss problem. In other words, if you looked at this bath of heat in a couple of million years, again, Doctor Who often goes to the end of the universe, right? They still have the TARDIS there, but actually it would just be a bath of cold heat. If you looked at this heat, you could actually never kind of work back in time and figure out what happened at early times. And scientists don't like that because whilst it might be very difficult to work out in practice what happens, we don't like the fact that in principle it's impossible to go from one time and work out what happened at earlier times. So, he concluded here that there was a real problem in kind of putting together Einstein's theory of what was going on in black holes with quantum physics. This is sort of 40 years ago, and this is a puzzle which is essentially what he and many others have spent their lives thinking about. So why did they spend so long thinking about it? So again, let's go back to the beginning of the 20th century. beginning of the 20th century is when people started to understand atomic physics, and this is, quantum physics. So quantum physics was a paradigm shift. So before quantum physics was developed, people could not understand why electrons just wouldn't fall into the positively charged protons. So electrons are negatively charged, they're attracted to the positively charged protons. This is a picture of an atom. And people just couldn't understand why that wouldn't happen. And of course quantum physics provided an answer because it said that there were various discrete orbits, and basically the electrons were not allowed to fall into the center of the atom. And this was a paradigm shift. It's a paradigm shift that we might not all be familiar with, but it's a paradigm shift and an understanding that controls all the technology in this room. Understanding this quantum physics was essential to understanding and controlling electrons and making electronic devices. So people have been fascinated by the issue of reconciling Einstein's theory of gravity with quantum physics to say, is there a paradigm shift here? Is there something fundamental we're missing about physics? And if we are missing some fundamental piece of physics, is that going to be crucial in 21st century, 22nd century technology? Okay. And so the conclusion is, over the last sort of 10 to 20 years, is yes, it does seem that we were actually missing a really fundamental understanding of physics. So there's, a really revolutionary new idea about how gravity works. So it kind of sounds crazy. Those of you who came on Monday night will have heard it, I think, in one of the talks then. It sounds kind of crazy. When people who first hear it, they think it's crazy. So the idea is the following, that gravity itself, so the gravity that we feel around us, we live in 3 spatial dimensions. We have 3 dimensions in this room. But that actually, fundamentally, the gravity that we feel, the things that we can sort of, if I drop a ball here, that this gravity can be described by a theory which doesn't have gravity in 1 less dimension. So 2 dimensions, 2 spatial dimensions is enough to describe our universe. So the picture on the right-hand side is sort of showing this. So inside our shell, we've got what we think is our 3-dimensional world. So we've got, black holes here, we've got strings, superstrings, and so on. We've got all kinds of different things. And what we're saying in holography is that actually when we want to calculate what happens, we can calculate everything that happens inside here just by working out things on this 2-dimensional boundary. So again, it sounds like a kind of completely crazy idea. So really, the 3rd dimension of our universe is an illusion. When it comes to sort of fundamentals, we really only have 2 dimensions. This is the idea. So it sounds kind of crazy, but actually, so it moves on. Actually, this idea reconciles the puzzle that Stephen had about, if you throw something into a black hole and it evaporates away, can you figure out eventually what you threw in? Can you kind of, in principle, work out the back history of the black hole? This idea immediately solves that problem. And it tells you something else, actually. So it tells you that space-time itself already becomes very quantum at the event horizon. So the traditional Einstein picture was, yes, you get to the event horizon, you fall in, maybe you see some strange kind of Doppler shifts in lights and so on, but basically you don't notice until you start getting pulled and stretched as you fall deeper inside. Holography says that space-time is already very, very quantum as you get to the event horizon. So for those of you at the back of the room, you don't see too much picture difference between this picture and the picture I showed before of a black hole. But if you're closer, you see, the artist, this is an artist from the New Scientist magazine, trying to sort of, in a sense, visualize the fact that at the horizon, it's a kind of quantum nature, there's a sort of fuzzy nature of space-time itself. That's where the fuzzball comes from. It's kind of a really bad name. I didn't choose the name, I have to say, but I had to stick with the name when other people had used it. Okay, so that's a little bit of a, an abstract sort of way of thinking of it. There's actually, I think, a much better way of thinking about what holography means for the event horizon, and that's where the connection to quantum computers comes in. So one way to sort of interpret holography is that the event horizon itself is like a giant computer hard disk. Okay, so In your laptop or your phone or your iPad, what does the computer hard disk do? It basically stores information as zeros and ones. So ultimately, all your apps on your iPad, ultimately they just convert the information into zeros and ones, right? And you do something that changes the zeros and ones. That's what a computer hard disk does. So what is happening on the black hole horizon is basically a giant computer hard disk. So again, this is another image of the black hole horizon. And this is again meant to illustrate that there's really nothing that goes inside. You go and hit this, and that's it, really. But this is an amazing computer hard disk. If Microsoft or Apple could make this, they would be really very, very happy. Because if you took a solar mass black hole, that's equivalent to about 10 to the 50 of the hard disks in a MacBook. And if you kind of scale this down to sort of ordinary masses, this is just a massively huge hard disk compared to what we have with current technology. So there's a kind of theorem in principle that black holes are actually the best hard disks that you could ever make in principle. This is the limit, right? This is the limit for the computer industry. The best computer you could ever make, the best storage you could ever get would be a black hole. So this is an interpretation of holography. So what is it? What's the deal about a quantum computer? So I said to you, a classical computer, basically it stores information in binary form, ones and zeros, and you tell it to do something, and it converts those binary numbers into a different binary number. But a quantum computer, the thing that's special there, is it takes a whole series of numbers, and it does a quantum trick, and it flips them all simultaneously. So a quantum computer, in principle, works much faster, at least for some processes. So there's a lot of investment into, it's not really, the next decade's technology. Again, it's looking to the late 21st century for building quantum computers, which would actually go much faster. So they would be using quantum physics to essentially manipulate the information faster. So instead of just writing each piece of information, changing each 1 and 0 separately, it will be flipping them all simultaneously with clever operations. So, Freeman Dyson comes from, very, very famous mathematician, physicist. He's now based in Princeton, but actually he came from this area, and he was educated in Winchester College. So one of the crazier things that Freeman Dyson has come up with over the years, he's done very many distinguished things, is the idea of looking for advanced civilizations by the fact that an advanced civilization would build a sphere around its star, around its sun, to harness all the energy from the sun. So he came up with the idea of, again, looking for such civilizations by looking for the existence of a sphere blacking out a star, and harnessing all of its energy. So perhaps this idea of building a Dyson sphere to use the black hole as a quantum computer, well, not perhaps, I think it does lie in the realms of science fiction. This is sort of image, again, which is taken from science fiction itself. But actually, the thought experiments that one can do with black holes give new insights into how you would make very good quantum computers. So the idea of throwing something into a black hole, doing the calculation and asking how it would change the state of the black hole sort of hard disk, this kind of gives you an insight into how you would, work with quantum computers. So I'm going to sort of end here with sort of this amazing connection, because we're going to hear in both talks tonight, all these fascinating experiments. So in this picture over here, we've got, the gravitational wave detector on the ground, all kinds of experiments, up in the sky, looking to image black holes very precisely, looking to understand, what happens when black holes collide using gravitational waves. But at the same time, this is really deeply connected with attempts to build quantum computers. So this is, the kind of a prototype quantum computer from a lab. And you would think that these two things are completely different science, but actually they're not. There's serious funding which comes to actually connect these two pieces together. I should mention I'm part of a collaboration which is called IT from Qubit. And this is sort of an image of a black hole. It's a strange kind of image. I think you can think of it as an image of the black hole's event horizon, and trying to connect this to controlling quantum bits of information in quantum computers. So it's a really exciting era for black hole physics, because with the new experiments underway, we're going to get a lot more understanding of the next period of time of the astrophysics of black hole, what's going on with these jets, with accretion disks and so on, with their formation. We're going to understand how they collide with each other, how the gravitational waves come out, all kinds of fascinating astrophysics questions. But particularly from the gravitational waves, we hope to understand more about the fundamental theory. So I should say, as we get more and more observations of black hole collisions, we will get more and more sensitive to what's actually going on at the black hole event horizon, be able to test, at least in part, some of these ideas of holography and the differences between the Einstein description of the horizon and this description of the horizon. And at the same time, we have this connection between the fundamental theory of black holes and quantum computers, which is certainly something that people like Stephen Hawking and Roger Penrose would never have dreamed of 50 years ago when they started thinking about the fundamental theory of black holes. So I'll stop there, thank you.
Thank you very, very much, Marika. It's a really amazing talk. Mind-blowing concepts of holography, and I'm sure that's going to spur off a lot of questions. I'd love to start somewhere with a question. There's one going. Yes, we've got one down at the front here.
So the idea of super interesting talk. Thanks very much. The idea of the holographic universe was originally postulated by David Bohm. Is that gaining a lot of traction these days?
I don't think it's his version of it which is gaining traction. So the sort of mainstream version comes from Gerhard Toft, who's a Nobel Prize winner, and Lenny Susskind. Actually, Lenny Susskind, I think, is quite a well-known popularizer of science. So I would recommend his books if you've seen them, or his videos on various places. So this came in sort of the early 90s. And then, in string theory, which is sort of the main attempt to reconcile gravity with quantum physics, this became sort of very concrete and very precise in sort of mid-late 90s. And now it's sort of, very much a mainstream idea. In a sense, almost the majority of papers, research papers in sort of high-energy theory, sort of quantum gravity type literature are using that idea. Yeah.
Have we got some more questions before we move on? Yes, we've got another one down the front here, Lizzie.
Well, I'm not a physicist, but I just wonder, I found it very interesting how you try to solve this sort of phase problem or loss of information through representing the black holes as a sphere, but not only the black holes, but also their environment. So I just was wondering, the implication of this would be that the attraction of the mass towards the center of the black hole is uniform, not only in the surface of the black hole, but also in the surroundings. I mean, is that possible? That is.
So the description of the black hole outside the event horizon is almost identical to what we expect from Einstein's theory. So it's virtually identical. So the effect on the space-time is almost identical to a level that we're very unlikely to be able to ever measure any difference compared to what Einstein said. So the main difference is that Einstein would have said that you can, in some sense, go in across the event horizon, and you still have some sort of classical physics sense of falling in. The notion of sort of going there, in your spaceship, this would make sense. And now the thing that's new is saying that, well, quantum physics is just so strong here that this notion of having 3 spatial directions, it just completely breaks down. You only have 2 spatial directions in quantum physics. The uncertainty of where you are is just so strong then almost your question isn't quite well defined because you've got to phrase it in a quantum sort of way. So almost space-time itself just behaves very differently once you've crossed inside the horizon. That's one way of saying it. Okay.
Thank you. Any more questions at the moment from Marika? I actually did have a question myself, if you don't mind. And I'm sorry if I misunderstood, but it seems that the holographic principle suggests quite a clear mechanism for writing to the hard disk, if you like, of the black hole, of throwing something in a particular place. But then I wasn't too sure on what is the mechanism, if there is one suggested, of reading out the data. How do you get it back again?
So indeed, so that's a more complicated thing to explain, but it's essentially your hard disk is getting smaller, but the bits which are sort of thrown out, they were in a definite kind of quantum state. So I can, because it's in a I know that the quantum state of the thing that comes out, then I will be able to figure out what came in. Yeah. But it's hardest to explain in sort of simple terms, I think.
Oh, well, thanks very much again, Marika, for a wonderful talk.